Hello and welcome to this lecture. We're going to continue with examples. I'm doing more and more examples just to convince you that doing powers with matrices is a little bit non-trivial and you may have to use some clever ideas. So these are examples of non-triangular matrices. So far we've seen only triangular. I'm going to give you examples of non-triangular and show you even more interesting things can happen. Here is this funny looking matrix, very symmetric sort of matrix. Okay, so if you do a squared, you get 2 0, a cubed you get 4 0, and then a power 4 you get 8, and you can easily guess what the pattern is, right? So this 0 1 0 0 1 0 in the middle is going to be the same, and then in these parts you go 1 2 4 8 etc. So that's 2 power k minus 1. So it's easy enough to guess. This is a power k. Okay, here's another example, very curious looking example: half 0 half 0 1 0 half 0 half. So all I did was I took these outer 4 and made it all half. And notice what happens here. A square remains the same. Wow. A square is the same. A power k is also the same. So a power k is the same as a. Like that. I don't know. Okay, it seems a little crazy. Just because I changed it to half, I got everything repeating. Okay, so notice how interesting these matrices are and why they behave like this is very mysterious. Here is another thing I've done. I took this, I made the middle one as 0 and then replaced these outer ones as -1. And guess what will happen if you do a square? You go to 0. Okay, so all sorts of strange patterns we're observing here. So it's going to get even stranger as you go to larger and larger cases. Okay, so but it turns out you can predict these things based on how these matrices are just by looking at it. You see some properties which will allow you to predict, and we badly need some nice characterization of why matrix powers behave in such fashion. Okay, so clearly if k is 0, if k is greater than 0. So what about general matrices? I've shown you so many examples, even with lower triangular and then square or in non-triangular matrices also. When you go to general case, n cross n, n can be very large. We know that A represents a linear operator T, A par K represents linear operator T par K, but still we need better insights. We want to be able to say what happens to this A par K. K grows, what happens? Does it blow up? Does it tend to some converging number? Does it stay the same? So does it repeat? Does it oscillate? Is it going to go to 0? Right? I would like to really know if A par K is going to go to 0. No? It's dramatic. So do these things happen? Okay. So another thing to keep in mind is given x, ax is very easy to evaluate. You just have to do the multiplication. I'm more interested in a par kx. What happens when a applies over and over again on x? Okay, does anything interesting happen? What happens to that? Okay, so that's something which is very important for us to understand. Okay, so finding this a par k in closed form and thinking about what it's going to be is not insightful and not easy. Okay, that's the big moral of all these calculations we saw. But we saw some nice patterns. It's nice to observe. We'll come back and try to explain those patterns. But nevertheless, just trying to do a power k in closed form is not going to take you far, particularly when a becomes large. If it goes to like 1000 by 1000, you're not going to be able to keep track of 10 power 6 values and how they change and all that. It's not going to be easy at all. Okay. Here is an important idea. So this idea will lead us to the next topic, which is a very, very, very important topic in all of matrix theory. And here is the simple idea. Okay, so it's always we use the same math approach, right? So instead of looking at a hard problem, you try to find some simple cases. See what happens in the simple case and see if the general case can reduce to that simple case. Here is a simple case. Suppose ax equals lambda x for some lambda. Okay, supposing you have an x which is not affected by a too much. Okay, in fact, it doesn't vary in direction. Okay, it varies only in magnitude. It gets multiplied by lambda, but in direction it remains the same. Okay, so x remains x. Of course, if lambda is negative, it will go to minus x, but sort of the same. Okay, so if ax equals lambda x for some lambda, then I'm going to argue finding a par kx is very, very easy. So if x is invariant under a, if x does not vary with a, does not vary when a applies on it, right? Ax becomes lambda x, some lambda, then a par kx is trivial to do. Why is that? A par kx is simply lambda per kx. It's just a number raised to the power. So if you do a squared, you multiply both sides, right? A square into x is lambda ax. And what is ax? Ax is lambda x again. So it just becomes lambda squared. So a par kx simply becomes lambda per k into x. Okay. So this is the core of our approach, right? So here is one vector for which I can find a par kx very, very easily. Is this enough? Okay, so we'll see that slowly, but this is a crucial next topic that we will study, eigenvalues and eigenvectors. We'll do that in the next week, but I want to show you how the motivation comes from. So the motivation is through these matrix powers and figuring out what happens to this a par k, what type of operator does it represent. And if you find vectors that are invariant under A, they're going to be sort of the same under a power k also, and that makes a power k and the matrix power easy to evaluate. So once you understand eigenvalue, eigenvector, all these curious cases we saw so far, what happens to all these kind of powers, why do they behave in this fashion, you can explain through eigenvalues and eigenvectors. So when you study them, we'll come back and look at these examples and see the eigenvalue, eigenvector explanation for why these behave.